And I'll put the link in the chat.
Mark, it's 8 o'clock. Maybe we can start.
Okay, great. Yes, I'll go ahead and get us started. So welcome, good morning, good afternoon, good evening, wherever you're calling in from. Today, welcome to the third day of the ACPC workshop. Today, we shift our focus from low cloud systems to deep convective systems. And my name's Michael Jensen from Brookhaven National Lab, and my co-organizer for these sessions is Jiwon Fan at Pacific Northwest National Lab. Today, we're going to have a series of 3 sessions focused on different deep convective topics. We're going to start with a session on marine aerosol influences on deep convection. Then later today, move to convective to global scale process studies, and then finally end with a session on tracer. Then tomorrow we'll have some quote poster sessions with a lot more time for discussion tomorrow. So with that, I want to go ahead and jump right into our sessions today so we can try to stay on time. Our first speaker today is going to be Lauren Zamora, who's going to be presenting on aerosols, especially from marine sources, affect deep convective cloud prevalence. With that, Laura, please, we see your slides just fine.
Okay, thank you. Thank you for having Ralph and I and giving us the opportunity to present our work. So there are many studies that suggest that deep convective clouds are impacted by aerosols in terms of cloud development, precipitation, and lifetime. And models have given us some mechanistic understanding of how that might happen, for example, through invigoration and other processes. But even so, aerosol effects aren't well constrained, especially over large spatial scales. And if we're trying to upscale observations of cloud interaction effects in the field, one particular challenge is that CCN and ice nucleating particles in background conditions are variable. And sometimes for ice nucleating particles, they're even high because of marine or terrestrial aerosol sources. And in addition, aerosol effects on clouds depend on meteorology and aerosol properties. So you can't always just compare clean conditions to polluted conditions and assume that the differences are going to tell you how clouds will respond across, for example, the entire tropics. Also, at least some of the effects associated with aerosols are driven by covariant meteorology. So for example, here you can see that Saharan dust is associated with fewer clouds and also hotter, drier, and windier and more stable conditions. So the convective cloud properties can be impacted by Saharan meteorology independent of whether or not dust, for example, is present. But we also know that covariant meteorology probably doesn't explain all of the aerosol associated effects because previous studies have tried to account for this covariation and still found a separate aerosol effect. So in our study, we were trying to better quantify region-wide aerosol effects on deep convective clouds. We used 7 million CloudSat deep convective cloud observations and also co-located aerosol and meteorological data from MERA-2 over several years. Having a large data set allows us to stratify in many dimensions, which offers a lot of statistical power to isolate the effects of the different variables like aerosols. We focused on nighttime data and that allows us to kind of reduce the confounding direct and semi-direct effects, and also really focus on microphysical changes from dust. So the question is, how do we successfully quantify the aerosol regional effects on cloud properties? Our approach is based on this equation here. We're approximating aerosol changes to a cloud property, such as cloud fraction. It could be also cloud droplet number, precipitation, or any factor, based on these three parameters here. The first parameter, C all, is the average cloud property in all conditions. So for example, average cloud fraction. This is an observable quantity. And from that, we can subtract the average cloud property in clean conditions. And as long as you have a way to quantify aerosol levels, that parameter is also observable. The first term here, it focuses on all conditions rather than polluted conditions. And I want to make that distinction because in doing so, our analysis can include aerosol-associated changes that happen at intermediate aerosol levels, and also different meteorological, spatial, and temporal scales. So the overall effects are going to be a lot less dramatic than they would be if we were comparing polluted conditions to clean conditions, but they'll also be more representative of what's going on a regional scale. For the second term here, C clean, we define clean conditions as clean with respect to an individual aerosol type, be it like dust or pollution or some other aerosol source. And we used a clean cutoff based on the 7.5% cleanest cases observed in the study area. So then from those two parameters, we have to subtract the changes to the cloud property caused by covariant meteorology. And this one's more tricky because it's not directly observable. Our approach to representing this change is to reduce this parameter to near zero by taking advantage of the really large sample sizes that are possible with satellite data, and stratifying them into small meteorological bins so that the conditions with and without aerosols can be compared without any major influence of covariant meteorology. And there's two reasons why we really like this approach. First, we don't need detailed upfront knowledge about the fraction of cloud active aerosols. And secondly, we don't need upfront knowledge about poorly constrained aerosol mediated freezing processes either, which makes this approach really nice for mixed phase clouds, for example, like deep convective clouds. The key here is that we need really large amounts of data, and with those large data sets, then we can stratify by meteorological factors finely enough to isolate the aerosol effects within meteorologically uniform bins. So here's just an example of a study. This is not in deep convective clouds, it's in the Arctic, but it just shows that, you know, kind of the method. This is similar to some other people have shown. Here we're looking at one specific altitude range and clouds that contain combustion aerosols. And these tend to have a lower cloud fraction as indicated by the blue compared to cases without combustion aerosols. So to get this, we just bin the cloud fraction data by meteorology using air's temperature and relative humidity and altitude. And then we use the aerosol concentration from a FlexPart model to compare the CloudSat property differences between all and clean background conditions over these different altitudes and surface types. So the parameters that we use to control for covariability depends on the system. That was in the Arctic. In the tropical North Atlantic, we actually used relative humidity, wind shear, and vertical updraft velocity for deep convective clouds. And a good way to select the meteorological parameters for stratifying the data is to select them based on which parameters are most predictive of the differences between all and clean conditions. So that way you isolate the drivers for covariant meteorology. And also the bins have to be small enough to adequately control for covariant meteorology. So I'll refer you to our paper for more detail on how we did that. Oops. So here are the data showing the changes in deep convective cloud prevalence over the North Atlantic using different cloud types using this method. So aerosol types. For the figure on the left here, we can see that CloudSat observations indicate that convective clouds occur about 4% of the time, with very little day or night difference. In other words, if you're looking up from the surface, about 4% of the time over the tropical North Atlantic, there's going to be a deep convective cloud overhead. The second plot shows whether different aerosol types are associated with changes in deep convective cloud prevalence compared to clean conditions relative to that aerosol type after we've controlled for meteorology. The different aerosol types include dust in orange and combustion aerosols in gray, sulfate in pink, and marine aerosols associated with DMS in green and associated with sea salt in blue. So after controlling for meteorology, aerosols of all types were associated with an increase in how often deep convective cloud cores were observed, somewhere between 30 and 87%, compared to clean conditions. And the effects were particularly large for aerosols associated with DMS in green. The plots to the right just show the uncertainty estimates here, and the point is just that the results were robust with respect to a variety of uncertainties we tested. And I have to refer you to our paper for more details on that. We also have to determine whether the changes that are associated with aerosols can actually be attributed to them. So for example, here in this figure, we're looking at changes associated with dust clouds. The y-axis shows the amount of dust-associated change that can be explained by various factors like temperature and lower tropospheric stability in black, and dust concentrations in orange. So basically, we used a generalized additive model to quantify how predictive each factor is of the increased deep convective cloud associated with dust. And we focused on data within meteorological bins to better understand what's driving this increase. And you can see that none of the meteorological factors, which are shown in black, explain more than around 2% of the remaining variability. So that's actually good. That means we've successfully accounted for meteorological covariation with the method. But then interestingly, the dust only explains around 5% of the remaining deviance, as shown by the orange bar. So this means that some other factor besides the meteorology and the dust is causing this large change in deep convective clouds that are associated with the dust. So it turns out that actually marine aerosol proxies, DMS and sea salt, help predict these dust-associated changes in deep convective clouds, and by a factor of 3 better within meteorological bins compared to any other factor. And as previously mentioned, associated factors like wind speed aren't causing this change because we already looked at that. It's in the black bars. So this suggests that marine aerosols and not associated meteorology are driving the changes merely associated with dust. So future studies really need to be careful not to misattribute marine aerosol related effects to the wrong type of aerosol. So thinking more about this finding, it's also possible that dust interactions with these marine aerosols matter. We know that if you sample marine air, you can pick up lots of gases and tiny particles that are CCN precursors. And a number of studies suggest that new particle formation in the tropics from marine aerosol precursors is a really important source of CCN. There have also been model studies predicting that dust could actually lower CCN concentrations on regional scales by up to 20% by acting as a potential coagulation sink for these CCN particles. So to test this, we looked at whether aerosols associated with DMS were associated with increased deep convective cloud prevalence within these meteorological bins. And it does appear that they are. So if you look at the plot, at this plot here on the right panel, it shows that deep convective clouds are more prevalent at high DMS levels than at low DMS levels once we control for meteorological covariability. In comparison, on the left panel, we can see that at low dust levels, deep convective prevalence can be high, but if you add high amounts of dust, the deep convective cloud prevalence gets lower. So in other words, high DMS levels are associated with more deep convective clouds, but dust is only associated with large changes in deep convective cloud prevalence when its concentrations are low. So maybe here's evidence that dust really is acting as a coagulation sink for these marine particles that otherwise would have formed the majority of CCN supply to deep convective clouds, whereas the dust itself is only a weak supplier of CCN. So we hypothesize that on large regional scales, dust may actually reduce CCN levels available to other clouds downstream, even though it by itself is actually a weak source of CCN. So in conclusion, we're presenting a method for quantifying aerosol impacts on clouds over large spatial and temporal scales. We showed some examples of how aerosols affect North Atlantic deep convective clouds. This method is nice because we don't need detailed upfront knowledge about the aerosol-mediated freezing processes or the fraction of cloud-active aerosols. And so that can give us important observational constraints on the cloud models, given large enough satellite data sets. But it's important to note that in order to attribute cloud property changes to different aerosol types, we have to demonstrate that covariant meteorology has been controlled for. And we showed one example of how to do that here. And it's also important to test which aerosol type is actually responsible for the observed cloud property changes. For example, the dusty conditions were associated with more prevalent deep convective clouds, but this association was actually more strongly driven by the marine aerosols transported with the dust. And in fact, the dust may actually reduce CCN by acting as a sink for marine CCN precursors over large spatial scales. So this is an example of how certain aerosol cloud interaction effects can best be observed over large spatial and temporal scales with remote sensing tools. And we're currently applying this approach to clouds in the Arctic, and we hope to have results on that soon. Thank you.
Okay, great. Thank you very much, Lauren. I think we have time for one quick question. I see Danny has a question in the chat. How did you determine cloud deep or deep cloud cover percentage?
We looked at the core of the deep convective cloud, and we looked at just the fraction of the area covered by that core over a given location, which would over the North Atlantic, basically.
Okay, I have a quick question about the aerosol or the aerosol categories you have there. For each pixel or each area, I assume you can identify one dominant aerosol type. If there were mixtures of aerosols, how would that impact your analysis?
Oh, so what we started out by looking at, we only isolated the effects with respect to one aerosol type to begin with. So for example, if we were looking at dust, we only looked at conditions clean with respect to dust. And we defined clean as the cleanest 7.5% of observations over the study area. And then for that first step, we ignored other aerosols that might be mixed in with it. Then afterwards, once we isolated heavy dust and low dust, or well, dust influence versus clean of dust conditions, then we looked at which factors were more predictive of the differences that we observed with dust. And when we did that, for example, with the dust, we found actually that it was the marine aerosols mixed with the dust that seemed to be more predictive of the eventual changes than it was of the dust itself.
Okay, great. Okay, thank you, Lauren. I see. It looks like there's more questions in the chat, so please check those out. But we have to move on. Our next speaker is Zhenjin Pan, who's going to talk about coarse sea spray inhibits thunderstorms.
Okay, yeah, thank you. Can you see my screen?
Yes, we can see and we can hear you fine.
Okay, yes, thank you. Hello, everyone. My name is Zhenxin Pan from Wuhan University and Harvard University. I'm honored to have the chance to report our study. So today my topic is coarse spray inhibits the thunderstorm. So we know the thunderstorm is one of the dangerous phenomena in the world. It can generate city destruction, aviation accident, flood, and fire. But we still know a little about the thunderstorm. A long-term unresolved question about the land ocean and contrast in thunderstorm, just like this figure. But it cannot totally explained by the land ocean difference in the dynamics. So question is, how much aerosol effects for the land storm, and can aerosol effects explain this land ocean contrast in thunderstorm? So in this study, we used the MSD Johnson satellite to track the whole lifetime of DCC, and really lighting data provides the real-time lighting throughout the DC lifetime. And the right figure shows our region of interest. And so next slide. So the best question is how to capture a deep convective system. So in this study, we identify the whole lifetime, whole DC lifetime based on the rainfall flux variation from the initiation of DCC to the dissipation of its envy, just like this case. This case is tracking the DCC cases with a lifetime of 25 hours. And you can see the bottom figure shows lightning variations in the timeline. Yeah, we can see the same pattern on the rainfall and the lightning in the DCC lifetime, just like increase and then decrease. And finally, we get about 76 DCC cases from the 2013-2017, and the detailed method is described in this paper, the GR paper. So firstly, we check the relationship between the rainfall amount of and the lightning density of DCC with the fire aerosol and the coarse salt. Yeah, we can see is the rainfall amount increased both of fire aerosol and coarse salt, just like this blue and the red line. And also the lightning density increased with the fire aerosol significantly. But this situation is totally opposite for the coarse salt. You can see this blue and the red arrow. So we get an assumption. also the fire aerosol enhance the lighting, cause it sort of awakens the sunstorm and the lightning by enhance the warm rain at the experience of the mixed phase precipitation. So this slide will fix the cause sort to isolate the effects of two aerosols, just like this figure. X-axis is the fire aerosol concentration, Y-axis is the lighting density, and different color indicates a different fixed cause sort concentration from blue to red line. Yeah, we can say whatever the cause sort concentration, i.e. the fire aerosol significantly enhance the lighting density, like this. Especially, you can say under the lower cause sort concentration, just like this blue line, the lighting density of ocean is close to that of land, just like this blue and red line is very close. So this slide shows the response of ice water pipes of kinetic core to the fire aerosol and cause sort. To answer this question, why is there a different response of lighting to the fire aerosol and cause sort? Yeah, you can see for the left figure, x-axis is fire aerosol, y-axis is ice water pipes of kinetic core, and different color indicates a different fixed cause sort concentration. You can see either the fire aerosol it was inhabits the warm rain, vigorous convection. So the resulting in some more ice water pipes and the lighting. But this situation is opposite for the cause sort. And this big x-axis is cause sort concentration, y-axis is IWP, and different color indicate different fixed fire aerosol. You can see either the cause sort, so it will enhance the warming by accelerating the collision and coalescence. It will weaken the convection, so it will resulting in less ice water pipes and the lighting. So this is academic for how the fire aerosol and the cause sort affect the lighting. Yeah, we can see either under the condition with the scaled cause sort, either the fire aerosol of ocean will significant enhance the lighting up to the factor of 22. It is too much. But under the much cause sort concentration condition, the other fire over ocean just slide enhance the lighting with a factor of 2.8. So evidently, the other cause sort can reduce the lighting by 19% over ocean, and this the effects of fires and cause sort on lighting are observed and comparable. Also check the effects of meteorology on the aerosol effects. So we find the effects of fires and cause sort on lighting are independent on the meteorology. Yeah. So yes, this is related public cases. Oh, okay. Yes, that's all.
Okay, great. Thank you very much, Zhengjing. Does anyone have questions for Zhengjing?
Can you hear me?
Yeah.
Yes, Xiaoxing, please.
Yeah, I just raise question. So your study region is quite broad across Atlantic from the west to the east, and fire mode, cause mode aerosol, they may come from different environment. Cause mode from of the coast of Africa, while the fine mode made from the western part. So their meteorology itself may be systematically different. How do you differentiate that?
Okay. Yeah, in this study, we used the Aerosol indicators aerosol with the particle radius below 1 micrometer, and the cost result is indicates aerosol from the sea spring with the radius beyond the 1 micrometer. It is not includes the dust aerosol.
No, my question is, in your study region, the data you are analyzing, the meteorology and the aerosol, they may be systematically different between the fine mode and the coarse mode aerosols, so that the effect of meteorology and the aerosol can be, correlated in that regard.
You mean the co-variation between two aerosols?
Yes.
Okay. Yeah. And yeah, just like this figure, where when we qualify the aerosol effect on the lighting, we fixed the cost result as a different beam.
Well, let me add that we also stratified to small beams of meteorology, like Zamora did in the previous presentation, and we found the same effects for the meteorology beams by Cape and by wind shear and similar kind of liquid water pass. Here it is.
Mm-hmm. Did you try to look at fine and coarse mode aerosol? Where do they come from? Whether they are all in the same region or they are systematically different? Say one in the Western Atlantic, one in the Eastern Atlantic. Their large scale meteorology can be very different.
So you mean the difference at a different region?
No, I mean, when you in this analysis, you just look at the data, disregard where they come from. If you look at your fine mode, coarse mode aerosol, just to examine where they are located, where they are from, and then you know what's the large scale meteorology, whether they are similar or different, that will help you to further constrain the effect of meteorology.
The coarse mode is just sea salt, so it must come from the sea.
Yes. Oh, so not including any dust.
No.
No, not include dust.
Okay.
Oh, okay.
So I think we need to move on. I'm going to suggest you could continue this discussion in the chat, please. And if folks have other questions for Zhengjin, please, there's some good discussion going on in the chat. But at this point, I'd like to move on. Thank you, Zhengjin, for your presentation. The next speaker is going to be Jiwen Fan, who's talking about impacts of ice nucleating particles from marine aerosols on mixed phase orographic clouds during the 2015 ACPC field campaign.
Can you see my screen okay?
Yes, Jiwen, you're good to go.
Okay, thank you. I'm not going to repeat the title. I want to thank my co-authors as listed here, particularly Yun Ning, who is at UCLA currently. So orographic precipitation, particularly slow, is very important to water supply, but the factors impacted are complicated and the models have difficulties to simulate it. Let me block. Yeah. So as reviewed in this review paper in 2019, that because of those very complex Touré effect and aerosol cloud orography interactions, winter precipitation in the West US is mainly come from orographic mixed phase clouds associated with atmospheric rivers. Those are the long and narrow corridors of strong wide wave transport associated with the extratropic cyclone. During Calwater and DOE's ACPEX field campaign in 2015, marine sea spray aerosols, or the main aerosol type, and marine as nucleated particles were dominant. This is in stark contrast with Calwater 2011, while dust was dominant. And the goal of this study is to provide process level understanding of how marine IMPs impact orographic mixed phase clouds and precipitation at different stages of AR events, because the thermodynamics are involving with AR at different AR stages. So the case was simulated is February 5th to 8th, 2015. This is a major AR occurring at that season, that winter season, with a high sea spray, marine sea spray aerosols and the low dust. This produced very heavy rain over the West US. There's 3 typical stages: before landfall, after landfall, and post AR. As you can see, before landfall, the typical feature is dry over the California, particularly below 5 kilometers. After AR, we have much increased moisture, but in the middle and high level, actually the moisture is reduced. And then the post AR, the typical feature is the temperature is lower, it's about 6 degrees lower. And I also want to note that after landfall, the atmosphere actually is more stable compared to pre-landfall, before landfall. So what we did is that we used Wolfgang coupled with a spectrum beam model to simulate this case, and the chemistry aerosols are explicitly simulated. This is at a resolution of 1 kilometer. Also, we're following what we did for the dust effect for Calwater 2011. We implemented this DeMott 2050 for dust IMPs and McCronsky 2018 for marine IMP for this study, to particularly for immersion freezing. And in the previous study, we found in the West US, those mixed phase clouds are mainly, the ice mainly comes from immersion freezing. So here is the evaluation for the ice, aerosol vertical profile and the aerosol composition. So I'm not going to have time to look at the details, but overall, it's reasonable with the emission sources from California air source board. So we, here is the evaluation with the precipitation. We have a lot of stations at the southern part, and from here you can see over this white box, we have this, for the 3 simulations, yeah, I forgot to mention, big is the original immersion freezes. So, and then DM50, of course, the dust line, and then DM15 and MC18 considers the dust and marine IMP effect. So here, yeah, we have better simulations in the southern part with the marine IMP considered. This is the aircraft for the post-cloud cell. And then it's difficult to simulate those clouds because the cloud cells are pretty small in post-AR. But the cloud phase as you can see from the DM50 MC18, we got about a similar value as observed, and the other two simulations basically simulate many liquid clouds. So the mixed phase state is better simulated. However, we do see we have much invigorated post-AR cell. So here, look at the marine IMP effect, which is compare DM50 MC18 with the DM15. As you can see, this is different stages. Before AR94, we have mean precipitation, and the dotted red line is the percentage change, and then a ratio of slow liquid water pass and ice water pass. Generally, we'll see at the pre-landfall and the post-AR, the model is the marine IMP effect is more significant compared after landfall. Also, the glaciation ratio, the same thing here, the changes is more significant at the stage 1 to stage 1 to 3, that too. But after AR landfall, we do see significant spillover effect, as shown clearly from here. So the load-proof spillover effect is more clearly seen from the mean or average of the cross section, and the main reason is because those ice and slow form over the windward side and advect to the lee side. So then on the cloud regimes, we separately look at the occurrence of the one cloud, which was cloud top below 30 and below below 0. For the mixed phase clouds, is the cloud top below -30 degrees Celsius. For deep, it's above with cloud top temperature above it, but the cloud bases for all the clouds are below 0. So maybe this one shows more clearly the relative changes. You can see over 3 stages. This is a different color of the box. We see shallow one cloud reduced and deep clouds occurrences are increased. So there's a significant cloud regime shifts, but it's more significant for deep clouds shift is more significant in the first and third stages. This is explaining why we see more impact on precipitation, slow ice water pass for these 2 stages. So then why IMP effect vary with different L stages? After AR landfall, remember we have drier mid and up atmosphere, like I showed earlier here, it also shows, and also we have more stable atmosphere. This could limit the enhancement of deep clouds and ice formation and glow by the IMPs. And then while we see much larger effect of immigration in the post-AR stage, that is here showing the dust concentration and also marine aerosols. You can see we have the steep marine aerosols, and those aerosols actually is larger in the later stage. And then correspondingly, the ice circulation rate also is much larger. So that's pretty all what I have. I want to emphasize that the marine IMP increase the precipitation slow and ice water pass more significantly actually at the before and post-AR stages, but a lot will spillover effect after AR landfall. And there's a significant cloud regime shift. And less significantly after AR is attributed to drier mid and up atmosphere and the more stable atmosphere. Thank you. And this study was accepted in the ACP, should be should be published very soon.
Okay, great. Thank you very much, Ji Wen. Do we have time for a question for Ji Wen?
I'll ask a quick question.
Okay.
G-Wind, does the model have grapple in it? Is it mixed? Does it have rhyme dice in it?
Yes. So here with the spectrum beam, we have the as slow grapple, and yeah. So basically, the low density aerosol, low density as particles is as slow, and the high density is grapple. And here we use a grapple version because we know we don't have hair. Thank you. Sorry, it's very early to me. I always drink a lot of coffee, but it was like.
Yeah, I was just asking because when we did experiments with the bulk microphysics, adding rhyme dice actually also shifted the timing of precipitation for these atmospheric rivers, or the location of it as well. So I was wondering if it added in there.
Yeah, here we did not do test because we for the spectrum beam we have this rhyming processes, and when conditions meet, it will have grapple. And in this case, I look at the grapple, the formation is low, so that's why we don't pay much attention. But there's plenty of slow.
So is it the fast SBM?
Yes.
Okay, great. I think we need to move on, Ji Wen. So thank you for the presentation. If you have further questions or discussion for Ji Wen, please use the chat. But we have one more talk in this session on influences of marine aerosols. So Edward Mansell is going to talk about simulated shipping lane aerosol effects with explicit electrification.
All right, well, thank you very much. So many of you are probably familiar with the paper by Thornton et al. 2017, where they were looking at lightning across the globe and noticed these enhancements in shipping lanes. And it was kind of an obvious conclusion that that would somehow be related to the emissions from the cargo ships. But exactly how that works is still a question. And then there was a modeling study by Blasi et al. Who tried to simulate this setup in a kind of radiative convective equilibrium modeling regime. And they found a couple things that there was this induced mesoscale circulation, there was some invigoration of the clouds, and there was a little bit more grapple mass in the shipping lane. And they took that as a possible signal for enhanced lightning. But there's no explicit electrification in that study, so you have to make inferences. And so this seemed like a really good case to apply our electrified version of WRF, called WRF-elec, and see if we can isolate just the microphysical effects, and as opposed to having the circulations. And so it's a pretty basic setup in WRF, doubly periodic domain. This is a fairly coarse 1 kilometer grid spacing for this preliminary work. There's a Diurnal Cycle. One thing is there's no feedback between the increased aerosol and radiation. And we use the NSSL 2-moment microphysics, because that's the one that's tied to the electrification scheme. And that's a fully 2-moment scheme with droplets, rain, ice crystals and grapple. And it also predicts the grapple density and hail density. And so for the CCN, there's a prediction of a very simple CCN concentration. It's not a spectrum, it's just a count of easily activated aerosols. And there's a restore function when droplets evaporate and clear, and also a slow restore in clear air to maintain a uniform distribution. Another feature is there's no saturation adjustment. There's just a sub-time step integration, condensation, and so we can get a residual supersaturation. And the main iso multiplication scheme here is the Hallett-Mossop process, Rime splintering, and that's dependent on larger droplets being present. We have a simplified three-dimensional lightning parameterization compared to what I've used otherwise in my work. And for this kind of case, it's typical long spin up and then see what differences we see. And in this preliminary work, I'm just using a 10-day period for convenience. And yeah, so this is my first foray into this kind of work. So appreciate the feedback here. So let's jump in, and this is just a time series of the 10 days with grapple mass. And just looking at this mess, you don't see a whole lot of difference between the different values of CCN concentration, except maybe at 1,000 it's a little bit higher. And if we just look at the hourly statistics, yeah, there's not really much change across, maybe just a little bit higher at 1,000 with a little more scatter, but kind of what we expect in this kind of a setup. And just a repeat of the hourly grapple mass. We also look at updraft volumes. Again, not much change. That's kind of what we expect in this RCE type of simulation. However, we do see some changes in the microphysics as we increase CCN, and this is also expected. There's reduced auto conversion, so we have slower rain formation, and so drop freezing into grapple is reduced. And correspondingly, we get, as we increase CCN, we get more creation of grapple through the Rime dice process. And overall, that maintains a fairly constant total number of grapple initiated per hour. So we don't see a big difference here that we would associate with a major change in lightning. And then just a quick aside, if we look more closely at the updraft profiles, we do see evidence of warm rain invigoration as we go from low to high CCN at low levels below the freezing level. We do see stronger updrafts, at least for these percentiles and updrafts greater than 2 meters per second. And again in the 99th. But then there's a corresponding reduction at mid and upper levels. Okay, and then on to lightning. So even though we don't see much difference in grapple and updraft, we do see quite a difference in the lightning. And in the time series on the left, and then summarized on the right with the hourly statistics going from 100 to 250, definitely see an increase, and then it's pretty much monotonic. So I tend to believe that there's a significant difference here between 100 and 250. And so what's behind this here again, the flash rate per hour. Well, the non-inductive charging rate is telling us how basically the collision rate between large and small ice particles that separate charge and then differentially sediment to give us charge layers and lightning. And the factor behind that is the ice multiplication increasing as we increase the CCN concentration, because we have about the same amount of grapple, at least throughout the domain, adding these extra ice crystals increases our collision rate, and that's the electrification rate and the lightning. And so that's the basics of what I've done so far. Like I said, it's preliminary work, haven't gotten into a lot of more details, but it's basically a 0th order test of whether just adding the CCN in this radiative convective equilibrium situation, can that give us greater lightning? And it does through this microphysical process, the ice multiplication. And basically, same amount of grapple, add more ice crystals, get more electrification. And so I would think there's likely a role for both of this mesoscale effect found by Blasi and this direct microphysical effect to explain lightning enhancement in the shipping lanes. And I would like to test with other ice crystal production processes, such as the freezing drop shattering and grapple collisions. And those are in process to add to the model. And I appreciate any suggestions or questions. Thanks.
Okay, great. Thank you very much, Ted. We have some time for questions. I see Michael Diamond has a question in the chat. Michael, do you want to just unmute yourself and ask that?
Yeah, this is a really interesting talk. I'm wondering how you think things might change if INP were enhanced in the ship plume in addition to CCN.
Yeah, that's a good question. I think I'd have to look at the settings that the INP parameterization here is the Myers. That's kind of my standard. And that has some issues, I know. But I also have a parameterization for the DeMott 2010 results. And in terms of INP, if you enhance that, what I've seen is that the INP are good for getting things started, but once you start getting a few drops to freeze and you start getting rhyming and you get the rhyme, the ice multiplication, that really takes over. So it'd be more a difference between no INP and some INP. If you add more, then it might get the process going a little faster. But I don't think it would make a big difference compared to the CCN. That might be a long answer. or not answer, but
other questions for Ted? So I'll ask a question. So this idea of the secondary ice processes playing an important role is interesting. And I'm thinking of this for applications for our tracer field campaign in Houston, where we have much larger baseline aerosol concentrations than you'll be getting in these shipping lanes. But we will see changes in the aerosol concentrations. Do you see this being something that, because you're in kind of the more pristine environment of the shipping lanes, that this is having a bigger impact, and might be muted in a location with higher aerosol concentrations, or do you have any thoughts on that?
Yeah, I mean, I can say that the nucleations scheme here is pretty simple, and so whatever CCN you put in can get pretty much activated. Whereas in reality, when you have really high concentrations, only a fraction of those will get activated. And that's what the Hu et al. Studied, looked at the droplet concentration around Houston. And I thought that was fairly consistent with what we found in our earlier study, the 2013 Mansell and Ziegler, where at about 1,500 droplet concentration, you started seeing a decrease in the lightning, and we attributed that to reduced ice multiplication. I think I have an extra slide here where, where I actually turned off the ice multiplication in these simulations. This is like the only plot I've made from those. And we see no lightning change with the CCN if we don't have that process.
Yeah. Okay, interesting. Thank you. Okay, so thank you for that presentation, Ted. That brings us to the end of this first session. So thank you to all the speakers. We're going to take a short break here. I think it looks like about to stay on time, we'll take a 5-minute break. Give Ji-Wen time to go get that cup of coffee, or give us all time to go get a cup of coffee, and we'll reconvene at the top of the hour. And yeah, Ji-Wen will convene the next session. Okay, see you in 5 minutes.
Thanks, Mac. Yeah. Let me get to the. Hi, Sean. Are you there?
Yep. Hi.
Hi. Yeah, Nini. So I think Sean, you want to do the timing. So give maybe 9 minutes. Give people warning on the time.
Yeah. Do you want me to say it out loud, or you just want me to put a chat?
Yeah, I would say probably say a lot.
Okay.
Not usually people when presenting will not pay attention to the chat.
Yeah. Okay. I'll say something at 9 minutes.
Okay.
Joanne, can you see my screen now?
Yes, I can
Okay.
see, but I see 2 screens right now.
Oh, okay.
Yeah.
Probably now.
Yes, perfect.
Cool. So yeah, I'll stop sharing and reshare in a minute.
Okay. Sean, do you want to also maybe pay attention to the questions in the chat? I will maybe pay attention to that, but let's.
I'll keep an eye on it, and I'll make sure that we know that there's one waiting in the chat if we have time.
Okay. Yeah. Yeah. So Nining, you will take a look. You will take notes, right? Not sure Ning is here. Oh, I think she probably go get coffee.
גיא, בהצלחה.
Thanks.
Andre, did you think it's a good idea? We also take a group photo, maybe at the last session, end of the session of today?
Sure. I wouldn't do it at the end of the session, maybe the next break, before the next break.
Okay, yeah, that's better probably. I don't know
And
what
tail
time.
off runs over, so I would do it right before the next break, probably. But sure.
Okay.
We've been up to 72, I think, is the high I've seen so far today.
Yeah, it's okay. I think we can get started for the second session today. We have 4 talks, and we have talks for convection at different regions in the world. My co-host and also notes taker for this session of Sean Freeman and Ning. Let's get the first talk started. Take it away. You read your title. Thank you.
Thank you. So yeah, I'd like to talk about the coupling between aerosol effect on subtropical and tropical clouds. We are all well aware of the scale separation issue between the global climate scale and general circulation scale and the much smaller cloud scale. And from a limited area cloud resolving model perspective, the scale separation means that we have to somehow represent the large scale effect on our limited area domain, or represent the boundary condition of this limited area domain. And this could be done in a few different ways. It could either be done by prescribing the boundary conditions, either in a more realistic or idealized manner, or we can even completely neglect the boundary conditions like we do in RCE simulations. But when we prescribe the boundary conditions, it means that we do not allow any interaction between the local clouds and the larger scale circulation and thermodynamic conditions. And it was shown before that in accounting for this coupling is important in order to have a full representation of aerosol effect on clouds. So what people have done before is using weak temperature gradient type of simulations that allow the large scale vertical velocity in the domain to react to the local perturbation, to the local clouds, and hence have some representation of the coupling between clouds and larger scale circulation. However, in a recent paper, we showed that weak temperature gradient type of simulation do not conserve water, and hence can have a very strong overestimation of the aerosol effect on the thermodynamic conditions. And more generally, we showed that how you represent, the way that you represent the boundary conditions in limited area cloud resolving simulations can determine the signal that you get, can determine the aerosol effect that you get. So Ideally, we would like to have some a cloud resolving setup that do both. So can both represent large scale circulation changes, but also conserve water. And currently, I'm working on trying to get such a setup. And what I'll show you today is really preliminary result in this direction. So the setup I'd like to propose here is composed of two different cloud resolving or LES domains that are online coupled to each other. One represents the tropical region with deep convective clouds, and the other represents the subtropics with shallow convective clouds. And there is some overturning circulation between those two domains, and they exchange water and energy in a way that try to mimic the Hadley circulation or the Walker circulation. The large-scale vertical velocity in the two domains is calculated based on a weak temperature gradient approximation in a way that conserves mass in the total system. And there is a water and energy exchange, as I said, between those two domains. There is obviously a lot of details of how exactly you do that. And I won't have time to go into all the details now, but I'll be happy to discuss it offline later on with anyone who is interested. I also think that it is important to close also the lower boundary, so to have a slab ocean or interactive SST in order to really conserve energy. But the preliminary result I'll show you today were done with a fixed SST and transient, relatively short simulations. In addition to enable interaction between clouds and the larger scale circulation and conserving water and energy, I hope that this setup will enable us to study intercloud regimes interactions. So in the tropics, we would expect that a perturbation in one of the tropical cloud regimes would also affect other cloud regimes. For example, if we perturb the subtropical clouds, we can imagine that it would also affect the energy and water advection from the subtropics to the tropics, and hence would have some effect on tropical clouds as well. And I hope that this setup would enable us to start to dig up those interactions. So how does it look like? Again, only initial results. So what we see here is the large scale forcing. So temperature advection, moisture advection, and large scale vertical velocity a long time in the subtropical domain and in the tropical domain. And what we see is that in the subtropics, we get general warming of the free troposphere, general drying, and generally subsidence, which is what we would expect to get in subtropics. And in the tropics, we see exactly the opposite of positive large-scale vertical velocity, moistening and cooling, again, as expected. And indeed, this setup produced deep convective clouds in the tropical domain and shallow convective clouds in the subtropical domain. And now that we have this setup up and running, we can start to perturb each domain and see what does it do to the clouds. In this case, I'm perturbing both of the domain at the same time, increasing the aerosol concentration in both of the domain. And what we see here is cloud and radiative properties a long time in the subtropics on the left and in the tropics on the right. And we can see that increasing aerosol concentration suppress rain in the subtropics, which is to be expected. We got some weak, fairly weak cloud adjustments, and we get a local cooling, which is contributed mostly by stronger reflection of short wave at the top of the atmosphere, but also we have some contribution from the long wave. In the tropics, we also get some cloud adjustment and a local cooling effect. And those results could either be driven by the local perturbation. So basically what we did in cloud resolving simulations until now. So you increase the aerosol concentration and you see what does it do to the clouds and radiative properties. Or it could be driven by the changes in the large scale circulation, large scale thermodynamic conditions, large scale forcing. And in order to distinguish between them, we can compare a coupled and uncoupled simulation. So what we see here is the response of the top of the atmosphere radiative flux so polluted minus clean to an increase in aerosol concentration. In red, we see an uncoupled simulations in the subtropics and in the tropics. And in blue, we see coupled simulation. And we can see that in the subtropics, turning on the coupling increased the local cooling effect by more than a factor of 2. But in the tropics, the results are much more significant. So we get from a local warming to a very strong local cooling. And this is related to the ice response to an increase in aerosol concentration. So in an uncoupled case, when we increase the aerosol concentration in the tropics, we get warm rain suppression, stronger vertical velocities, stronger mass flux to the upper atmosphere. That increase the ice water path and hence have a strong long wave warming effect that was shown before. However, when we turn on the coupling to the larger scale and to the subtropics, we get this increase in ice water path is replaced by a weak decrease in ice water path, and hence we get a very strong cooling effect due to shortwave changes. And why do we get this decrease in ice water path? It is because of the changes in the large scale circulation. So what we see here is the difference in large scale forcing between a high and a low coupled simulation. Again, for the subtropics at the upper line and for the tropics at the bottom. And under polluted conditions, we see that above the boundary layer, we get a general weaker updraft, so relative subsidence under polluted conditions, and relative drying and warming of the free troposphere. This weaker large-scale vertical velocity, relative drying and warming, it was what causes the reduction in the ice water path and hence cancel out this long wave effect. And why do we get this reduction in vertical velocity? It is because of the rain suppression in the subtropics. So aerosol suppressed rain in the subtropics, the air that is advected from the subtropics to the tropics now is colder under polluted conditions. And if you cool the tropical atmosphere from a weak temperature gradient approximation, we get weaker large-scale vertical velocities and hence also decrease in the ice water path.
1 minute left.
But yeah, by that I'll wrap up. I'll just summarize by saying that what I'm trying to do here is develop a setup, a numerical setup that will enable us to examine interaction between clouds and aerosol in larger scale circulation, but still conserving water and energy and resolving clouds in high temporal and spatial resolution. Thank you.
Any questions? Let me see.
I should say that it's really a work in progress, so I'd be happy to get any comments, questions, and so on. That would be great.
So
Guy,
Danny has a question. Yeah, Danny.
yeah. Did you try to perturb only the tropical deep convection or the stratocumulus regime separately and see what happens?
Yes. I did it. I didn't put it here, but if I keep the tropical domain the same and only perturb the subtropical domain, I see the same response. So suppressing rain in the subtropical domain because of aerosols advect colder air to the tropics and reduce the large-scale vertical velocity in the tropics, even for the same aerosols in the tropics.
And vice versa?
Yes, but there are some nonlinearities there that I don't fully understand, and I think it will be really nice to try to understand. It's not exactly linear. It depends on the it depends on the aerosol conditions in the tropics.
Thanks.
Okay. Let's move on and feel free to put your questions in the chat. Thank you, Guy. Okay, so our next talk is from Gayatri Kokoning. She will talk about how robust is aerosol invigoration effect over the Indian subcontinent. I think Gayatri is sharing the screen.
Yeah, just a minute. Am I audible?
Yes, perfect now.
Okay, yeah, thank you. So, talk about aerosol immigration effect over Indian subcontinent. So, it's not going to the next. Okay, yes. So first I'll discuss about the previous case study, which is already published. So here we observed a deep convective cloud, which was profiled by an aircraft till 8 kilometers. We can see the cloud profile here. And this case was simulated with WRF model using spectral bin microphysics scheme for 100,000 and 3,000 initial CCN concentration. And the small box we can see in the domain C, which is written as study region. And the inner domain that is pointed as domain 3. Okay. So from that study, what we found out is that for a small region, for a single cloud analysis with increasing CCN concentration, liquid water path and ice water path were increased, and we saw almost 20% increase in precipitation. But when we saw the increase in precipitation over the whole inner domain, it was only just 5%. Okay. And we did see convective invigoration over the study region. Like for high CCN simulation, we can see quite stronger updrafts. But when we look at the PDF of updrafts over the whole domain, then it was not much distinct. In fact, for higher altitudes, the updrafts for high CCN simulations were lower compared to the clean simulation. So we decided to work more on this aspect, and we simulated 4 more cases. So now I have total 5 cases with this configuration. I have 3 domains, and I'm presenting results for the innermost domains. And this is the experimental setup, and I'm using bin microphysics scheme. The clean simulation has 100 centimeter CCN concentration, and the polluted case has a 3,000 cubic centimeter CCN concentration. And this simulation has been ran for 24 hours, and the first 6 hours we excluded as a spin-up time. So with bin microphysics, a 24-hour simulation for 5 cases I'm presenting here. So these are the 5 cases I selected. As we know, the environment also has a strong effect on the outcome of aerosol impact on precipitation. So we chose 5 cases such that they had different environment. So first case here, it was a withdrawal phase of southwest monsoon. Then case 2 and case 3 were quite dry environment, and case 4 and case 5 were after the onset of southwest monsoon, northeast monsoon. Sorry. So case 4 and case 5 have had quite moist environment in that. And we chose these 5 cases because we had aircraft observations for those 5 cases. And here at first glance also we can see this is for clean, and the bottom panel is for polluted. We can see the disappearance of shallow clouds over the ocean, and we saw some intense deep convection in the polluted environment. So this is the environment profiles, some high relative humidity after the onset of monsoon, and different wind shear and velocity was also quite different. Okay, so then first we compared the simulations with the aircraft observation. So blue is the model mean and red is model max, and gray dots represent the aircraft observation from Kypex. So we can see first panel is the liquid water content, and we can see quite high liquid water values, especially super cooled liquid above freezing level, greater than almost 1 gram per meter cube, and ice was quite high, ice content also. And the model simulated well all the features of cloud microphysics. Okay, so then let us look at the cloud fraction average over the whole domain, and we can see that cloud fraction for shallow clouds or the lower level clouds was decreased in all 5 cases, and for higher clouds, mid-level and high clouds, it was increased consistently. And when you look at the liquid water path, PDF of liquid water path, we can see the contribution from the lower LWP, that is from shallow clouds, is less compared to the high liquid water path for all cases. Okay, so then we decided to look at only the deep convective cores to understand aerosol cloud interaction for the deep clouds only. So for this, we use this criteria from Pan et al. 2013. So first we identified cloudy points, and then cloud bases who has warm cloud base, only those were selected, and single cloud layer thickness greater than 8 km, and updrafts were greater than 1 meter per second. So for the only those cloud cores, so this is the cloud depth frequency distribution, and we can see for the higher pollution, cloud depth was more for deeper clouds, and for comparatively not so deep clouds, like for 8 km and in, it was smaller for high pollution cases. So we can say that increasing the frequency of deeper clouds is more in polluted environment. And then we looked at the CFI diagrams for different microphysical parameters. So first one is cloud liquid water content, where we can see significant increase in cloud liquid water for polluted simulation at lower levels, as well as in the supercooled region. And we also see the ice mass content has increased significantly in polluted case. Then snow mass also has increased compared to clean case for all 5 cases, and graupel mass as well showed an increase. So how it affects the precipitation? So when we segregated the precipitation into 4 different categories, as for light rain, we saw the reduction in precipitation, light and moderate rain for all 5 cases, and for few cases showed like this one and this one, a few cases showed increase in precipitation for heavy rain category, but consistently all 5 cases shown increase in extreme precipitation, that is greater than 50 micrometer. So aerosol indirect effects associated with shallow clouds may offset for the aerosol indirect effects associated with deep convection, and thus it is giving a more moderate response. So whether this precipitation came from the aerosol invigoration effect, that we wanted to check. So this is the CFI diagram of updrafts, and we can see first panel is for 100 ccn and second is for 3000, and except one case, this is the last one, there was no significant difference in the updrafts, and these are the greater than 1 meter per second updrafts were considered only. But only one case showed significant increase in updraft in polluted environment, but all other cases didn't show much change. And this is precipitating downdrafts I have presented, and all cases show significantly more precipitating downdrafts in polluted environment, and even they were stronger for few cases. And this can give a message that condensate loading, as we saw all the ice, snow, graupel, and cloud liquid water was more in polluted environment, and precipitating downdrafts also more. So condensate loading was more in general, and that led to increasing precipitation instead of invigoration. So this is the initial analysis. So we have come to conclusions that, so when we look at single clouds, then there was enhanced mixed phase processes and increase in dynamics, like more updraft, and increase in precipitation was 20%. But when we look at a larger area and more convective system, there was enhancement in condensate cloud fraction, deeper cloud cores, but there was no prominent impact on dynamics. And when you look at the average precipitation, the increase was just 5 to 7%. So the takeaway message from this is, there were no significant changes in the strong updrafts in clean and polluted runs, and the difference in precipitation are greatly impacted by how early precipitation starts and warm clouds depth. Also, the clouds were at different stages because we considered the whole simulation period, so that may affect the results. And aerosol indirect effects associated with shallow clouds in tropics may offset and compensate for the effects associated with deep convection system. And does it produce a more domain-wide moderate response? So, thank you.
Thank you, Gayatri. Let's see, let me check the chat. There's any questions for Gayatri? Okay.
There's one from Ross Herbert in the chat.
Oh, okay, go ahead.
Hi, great talk. Did you look at how the number of deep convective cores changed as well? So I'm sort of thinking, do you end up with fewer deep convective cores?
Right. No, I haven't looked at it, but I'll surely check it. Like number of deep cores, how much were there in the polluted clouds, right? Polluted simulation.
Yeah, it'd be interesting.
Yes,
So
no, I haven't looked at it yet.
Yeah, it'd be interesting. Thank you.
Did you include radiative effects of the aerosols?
Not explicitly, but we prescribed the radiative scheme in the model while running. So it takes care of the interaction, but not explicitly we didn't include.
Okay, Gary, I have maybe two quick comments. One is, yeah, it's very last thing you basically seeing these results very consistent with what we see in 2013 paper. So one comment is about, I didn't see you show you considered open canopy models. So the urbanization effect over that region could be important. The second is the aerosol size distribution is very important. I didn't know if you include any ultrafine aerosol particles.
No. This is the whatever prescribed size distribution is there in bin microphysics form that is there. But we are doing some work right now where we are planning to change the ultrafine particles because we know that they are important, and from our aircraft observations also we have found they are important and they affect clouds very much. So, but this is the undergoing work currently, so I'm planning to extend it further with that.
Okay, great. Thank you. Let's move on. Our next talk is William Jones. He will talk about the life cycle of deep convective cores and the associated M1 class observed by GS16. William, are you there? Let's see.
Yes, thank you very much, Juan. Yes, so as introduced, we've been observing and looking into growing deep convection and deep convective clouds that we see using the ABI instrument aboard GO16, and linking those to the AMBO clouds and then using that to study the overall lifetime. So this research performed by myself and Philip Steer. I'd like to also acknowledge Matt Christensen, who was involved in prior research to this that led on to this. So starting off, if we just kind of have a look at the life cycle of deep convective clouds, we can generally divide it into 3 stages. So we have the growing stage of deep convection, which is dominated by the vertical development of the growing deep convective core. We then move into the mature phase once we hit the level of neutral buoyancy, which is dominated by the horizontal growth and formation of the AMBO cloud. And then after the cessation of the convective core, we see the dissipating phase where that AMBO cloud breaks up and dissipates. So most studies that look into using geostationary satellites to detect and track convection primarily focus on this mature stage of the AMBO cloud. And that's because it's the most reliable feature to track in geostationary observations, particularly in IR, because you have a strong contrast between the thick AMBO cloud in the background, and you also have a large AMBO cloud in comparison to the motion of the cloud, so it's easier to isolate and track individual clouds. But arguably of interest for studying the behavior of deep convection, the growing stage and the dissipating stage are more important to delving into interactions and feedbacks of deep convection. So to approach this, we developed a novel method for detecting and tracking deep convective clouds that starts with detecting the growing cores of deep convective clouds by detecting regions of rapidly cooling cloud top temperature and brightness temperature. And then we assign those as our detected growing cores, and then we continue to detect the anvil clouds that are associated with those cores, even after the growing core is no longer visible. So we detect the full lifetime of both the thick anvil cloud and the thin anvil associated with that. And so we've performed this tracking for currently a year of data from the continental United States region of the GO16 ABI. And that's provided us with in excess of 80,000 detected growing deep convective cloud cores and 22,000 anvils. And it should be noted here that we have fewer anvils because we can associate multiple growing cores with a single anvil cloud. So we have both isolated convective cases where we see a single core developing into a single anvil cloud. We also have more complex multi-core convection where we associate multiple growing cores with one large anvil cloud shield. So to begin looking at the spatial distribution of our detected growing cores and how that changes with the seasons, we see the wintertime and springtime convection are both fairly low as expected, but also dominated by this kind of the Western orographic and Great Plains convection. And then we shift into a summertime region where we see much more of the tropical convection over the coastal regions and adjoining ocean. And then in autumn, we reduce that tropical convection, but we still see an increased rate over the oceans due to the time lag of surface heating. Looking at the diurnal cycle, we see some quite strong contrasts, most notably the land-sea contrast between the average time of day that we detect convection. We also see later convection over the Great Plains, particularly the northern Great Plains, and there's a shift in the time of detected growing convection nearer the coast, where we see earlier times, which we expect can be attributed to a sea breeze effect. And just to quantify that, we can look at how the average time that we detect these growing deep convective clouds changes with distance from the coast. And we see quite a clear change of earlier time of detection close to the coast, up to around 200 to 250 kilometers from the coastline. To delve into these effects more clearly, we then split up our region of analysis into 4 regions. So we have the ocean region covering the Gulf of Mexico and the East Atlantic, the coastal region, which is spanning up to 200 kilometers from that coast, and then 2 inland regions, the Great Plains and the Midwest, which have a 50-kilometer buffer from that coastal region to prevent spillover of those sea breeze effects on the diurnal cycle. So looking at the diurnal cycle within these regions, we again see the strong contrast between the land and sea, where we see the ocean convection is much more consistent throughout the daytime, but has a peak in the morning hours, whereas the convection over land peaks in the afternoon. We see the earlier peak in the coastal convection, and then also in the Great Plains, we see more convection occurring over the nighttime, particularly in the evening. But when we start looking into the behavior of these individual cores, we see that the lifetime of the growing phase, the deep convection, is actually very similar in all these regions. However, when we look at the detected cooling rates, a measure of the intensity of the convective growth, we see in the Great Plains that this is actually, we have a longer tail, so we have higher cooling rates observed. And when we look at the individual regions, we see there's a quite strong correlation between the lifetime of the core and the maximum cooling rate observed. But this doesn't cross over into comparisons between the regions, because as we move further north, we have warmer tropopause temperatures and a lower tropopause, which means that actually this more rapid cooling rate results in the growing cloud reaching the level of neutral buoyancy faster, and that's when we stop detecting the growing phase. So although we can use the lifetime of the cores as a proxy for the how intense the convection is within local regions which have similar meteorology, the differences in the meteorology between different regions means that actually this proxy becomes less useful. And then moving on to anvils, we can look at how we associate these growing deep convective clouds with the anvil clouds, and looking at the frequency of both single and then multi-core convection anvil clouds by the number of cores that we associate with them. We also have a number of deep convective cores which we don't see any significant anvil cloud growth. So we don't see growth of the anvil cloud after the end of the growing phase. And then breaking down these life cycles, the anvils, into different stages. So we start with the typical lifetime of each of the individual growing cores, which is actually very similar between all the cases. And we don't see any significant differences between the growing deep convective cloud cores that contribute to isolated convection to those of multi-core convection. However, when we look at the time to reaching the maximum extent of the anvil clouds at the end of the mature phase, and then the time to dissipation of both the thick anvil and the thin anvil, we see that these proportionally increase with the number of cores that we detect associated with each anvil cloud. Possibly the most interesting change is when we see the coldest brightness temperatures within the anvil cloud, and that we actually see a reasonably consistent time lag between the coldest brightness temperatures being observed and the end of the maximum extent of the anvil clouds, the end of the mature phase. And what this means is that for isolated deep convection, we see those coldest brightness temperatures very soon after the end of the growing phase. But for multi-core convection, we see those cold brightness temperatures much later in the evolution of the anvil cloud. And because the diurnal cycle of the development of these growing cores is very similar between these, that means we actually have that time period for the coldest brightness temperature observations varies quite significantly based on how complex the convective clouds are.
1 minute left.
So to wrap up, we see, using this year of data, we see quite large changes in both seasonal and diurnal cycles, which are connected to regional differences in convection. And this means that when looking within those regions, we can use proxies for variables such as the intensification of convection. So for we need to take into account the difference between different regions when comparing between those cases. And then we see interesting behavior in the case of isolated versus multi-core convection, in that even though the individual cores of these cases show little significant difference in the growing phase, we see large changes in the lifetime of the overall anvil cloud, probably due to dynamical processes occurring due to the aggregated convection. Thank you very much.
Okay, thank you, Winning. Any questions?
Yes.
Yeah. Oh, Danny, go ahead.
Yeah. If you go 2 slides back, we see a large difference. No, 1 slide forward. Yeah, you see a large time difference between the minimum temperature of the anvil and the minimum temperature of the and the time of the core. Does it mean that the anvil gets colder than the core, or there are cores that colder cores that occur later?
So it's part of both. So one thing to be clear is that what we're detecting as the core here is just the growing phase of the core, so that we will continue, there will be continued convective updrafts within the anvil cloud after the end of our detection of the growing core. But that's just because once that reaches that level of neutral buoyancy, we can't detect those rapid cooling rates of the cloud core during the growing phase. So there will be convective activity continuing during that time. And yes, there will be a time lag between some of the cores occurring during these multi-core anvils. It's just a more complicated analysis to look at how the separation both in time and space of the different cores contributes to the overall anvil properties.
Thank you.
I think Jesse has a question.
Yeah, very quick one. So I see in the early slides you show a density plot of the identified deep convective cores. Can you go back to the slide? Because I'm trying to understand when I compare this with the US, lightning density, especially at like an LDN. I see there's a. Oh, this is okay. So this is so why the like from March to May or from December to February, you always see a peak, near the mountain area, but the Great Plains and all the south east of US has lower core frequencies, like are indicating the convection is less there, but the lightning density is really highest in the southeast.
So probably one thing to be clear about there is that this is, I suppose I wouldn't expect the number of lightning strikes per observed core to be unique. We'll need to look into it further, but I think this is partly due to some of the synoptic changes. I think a lot of this is shorter lifetime overall. The anvils detected kind of over these mountain regions in winter and spring. So there may not be the same sustained convection, therefore this number of lightning flashes in these storms compared to those occurring over the Great Plains and the Southwest. Yeah.
Okay, thank you. We can talk more.
Yeah, it is something we want to look into it more. We do have the lightning data for each of these anvils. So
right, it would be interesting if you
GLM. And how many flashes
to your tracked course. That
yeah, I think we need to probably move on the questions offline. Let's move ahead to our last talk of the session from Sonia Nashtrap. I will let her just go ahead with, go ahead, Sonia.
Okay, are you seeing the screen correctly?
Yes.
Okay, thank you.
Mm-hmm.
Hello, everyone. Thanks for letting us share our recent results on investigating the effects of CCN on the timing of convective cold pool initiation during some cases from the CAPDI field campaign. I should point out that most of this work was done by a master's student in my group, Toby Ross. So cold pools, as many of you know, are these mesoscale regions of cool air forming beneath precipitating convection. They're driven by latent cooling from phase changes as hydrometers descend towards the surface. They play a crucial role in organizing deep convection. They can initiate convection along the outflow boundaries, or also called the gust front. They can also suppress convection in their interior by stabilizing the lower atmosphere. They are vital to shallow to deep transition of convection and also maintenance of some long-lived convective systems. And of course, because they can help excite additional convection and precipitation, they can be an important component of the hydrological cycle. Now, recently, larger scale weather and climate models have begun to try to parameterize cold pools and their effects. But they do it quite simply yet, and they often still need to disregard the underlying microphysics that initiate and maintain them. And specifically, what we were kind of curious about investigating is what are the CCN effects on the precipitation production, and how would that feed into cold pools? And so should cold pools parameterizations consider CCN effects? What kind of led us into this idea was a previous study where this was just some idealized modeling of a mesoscale convective system. And on the vertical axis here is the timing of the first cold pool. And we had done just a variety of simulations, just trying to get a bunch of realizations, tweaking the microphysics. And as you can see, the one change here that I've enclosed in the box that made a big difference was increasing the CCN in this idealized simulation, greatly increased the onset of the cold pool. And so our working hypothesis was that cold pools are delayed when storms ingest more CCN, and this is a result of the slower warm rain process. Now, I'm not trying to imply that all the rain that falls from these clouds is due to warm rain, but we think it's playing a role here. And so, again, our overarching goal is to try to figure out if CCN amounts, in the local area should be included in these cold pool parameterizations. So we were able to use some cases recently collected during the cacti field campaign in Argentina. They had a research aircraft during part of the field campaign that measured CCN near the clouds, including near the cloud bases, and also then took in situ measurements inside the developing cumuli, and where we could kind of document the speed of the warm rain process. Then, of course, the aircraft couldn't fly through the deeper systems, but we could switch to radar then, and we could look at the radar evolution of this deep convection and also the onset of the first cold pool. And I should mention, we're really interested here in the very first cold pool. We could also had made use of surface measurements during this field campaign to kind of document the cold pool characteristics. And finally, the radio signs we could use to document the storm environments for some numerical modeling that I'm also going to show. We also used some Relombico field campaign that was co-located. So let's just briefly talk about the initial shallow convection that the aircraft sampled. And basically, as you would expect, the speed of the warm rain process was inversely proportional to the CCN measured. So I'm just highlighting 3 of the cases here. We looked at all of them. And in these 3 cases, we kind of have higher value of CCN, a lower value of CCN, and maybe like what I'll call a middle value. And so in the bottom plots here, what I'm showing are the aircraft data of the hydrometeors sampled by the aircraft inside the shallow convection. And so if you just focus on the red dots here in the red data, this is from the 2DS. So we're looking at drops greater than 50 microns in diameter, essentially looking at when you're getting collision coalescence started and then into the development of drizzle and precipitation. And as you can expected for the case with the least CCN, we're getting values up to like 100 per liter in these clouds. In the highest CCN case, unfortunately, we just had some lower values here, but you can see that we only get to a few per liter of particles sensed on the 2DS, and then the middle CCN case was in between. So this was all as expected. So now we're going to jump to the deeper convection, though, observed during cacti. And in fact, there was no clear relationship between the CCN and the timing of the first cold pool. And here I'm emphasizing the first one. That's what we're trying to figure out, when the convective parameterization should start saying, boom, the cold pool starts now. So our hypothesis was that the cold pool should be delayed with increasing CCN. And so, with 3 cases, yes, this is the problem, right? These were the only 3 cases where we could really definitely say that we were seeing the cold pool, the first one in the observations. And so these first 2 cases start to suggest a trend. And then, of course, this last case on 5 December doesn't. It was the quickest cold pool, despite the fact that it had the highest amount of CCN. Now, as you're probably already worried about and thinking about, were environmental parameters consistent among these 3 cases? No, of course not. They varied significantly, the CAPE and the shear. And in fact, I'll show that this last case on December 5th basically had environments supporting supercell thunderstorms, while these other 2 cases did not. And that's going to have an important role to play here. So I want to jump quickly to some numerical modeling experiments. These were done, idealized simulations with CM1 with NSSL 2-moment microphysics. We have control simulations for these 2 dates, 4 and 5 December, in bold, and those were the actual measured, CCN values at 1% supersaturation. And then we, halved and quartered those values in a set of simulations, as well as 1.5 and twice those values, just to kind of see the sensitivity of the cold pool initiation time to these different values of CCN. We define the cold pools by the -1 Kelvin theta perturbation, and those here shown here in the black outline at the lowest model level, which was here 100 meters. So just real quickly, what these simulations look like. The 4 December simulation, like I said, it's kind of like an ordinary thunderstorm, so to speak. And you see the appearance of the first cold pool here around 80 minutes or so. The supercell on 5 December, however, it intensifies much more quickly. We see an earlier cold pool formation there for the 5 December, despite the fact that it had much higher CCN values. Now, if we look across the spectrum of all those sensitivity tests with different CCN values for the 4 December case, the ordinary thunderstorm, and the 5 December, the supercell, there is a nice relationship between the cold pool initiation time being delayed as CCN increases when you're kind of talking about an ordinary thunderstorm, and it starts to become that way for a supercell, and then it just kind of levels out, okay? And so we're saying that the storm morphology here is mediating this response. And we saw this in numerous other aspects of the cold pool as well. So it's kind of less sensitive to CCN. And I think Sue Vandenhever, her group, and others have shown that supercells tend to be less susceptible to CCN effects. For both environments, we found the greatest sensitivity, at the lowest values for these environments. And, these lowest CCN values, whether those would ever be found in central Argentina, it's unlikely, but still we were just kind of doing it to see the effects. So, okay, but is this really all about the warm rain process? I kind of said we'd get back to this. So it is, but it's through its influence on graupel formation, as some of the other talks have kind of shown today. So if you have a slower warm rain process with increasing CCN, all right, then these are the 95th percentiles of hydrometers in updrafts early in the simulation. All right, and so you can see then for these higher CCN runs, the green, the red, the purple, all right, you have more cloud water, of course, and you have much less rainwater because, slower auto conversion. So we're slowing the warm rain process as expected. And of course, this impacts the ice processes above, and you have less graupel initially in these updrafts. And then this is because of fewer raindrops for immersion freezing. So it takes longer for the graupel to grow. You also have more ice and snow initially. And that's due to this extra cloud water that wasn't converted to rainwater. And then this graupel pathway dominates the rainfall at the ground. So, early on, just the low CCN runs have rain reaching the ground, and this is when the cold pool has initiated. These are in the downdrafts, I should mention now, sorry, these hydrometers. But by 85 minutes, the cold pool had initiated in all the runs. And, we've done the tests and look at this, and this rainfall is not warm rain, okay? It's actually melted graupel. So it's going through the graupel, pathway to then cause the cold pool. So the sequence of events in these idealized simulations appears to be more CCN delays the initial graupel production, which is going to delay the initial surface rainfall and then delay the first cold pool. So despite, okay, I'm finishing up. Despite the early research flights on the early convection showing that there was, clear connection between the warm rain process being started and the CCN, there was no clear relationship when you look at cold pool onset time in the observations. But we think this is due to the fact that some of these were being modulated by the storm morphology, differences in supercells and ordinary thunderstorms in this example. The microphysical pathway, like I said, is basically increased CCN, decreases supercooled rain, delays the graupel, delays the surface rainfall from the melting graupel, and thus delays the cold pool. Thanks for listening. I'd be happy to take any questions.
Okay, thanks, Sonia. Any questions? I think Sue has one in the chat. Sue, did you want to go ahead?
Yeah, maybe I can just speak to it, Jiren, that might be easier. Hey, Sonia, thanks for a great talk. You talked about the delay in the warm rain process, right, in terms of it showing up at the surface later on. Have you looked at all of the impacts as well on the drop size distributions and hence evaporation? And I know that doesn't necessarily talk to the first cold pools, but it does talk to the intensity later on.
Yeah, so I didn't have time to show this. Well, yeah. We actually just did latent cooling budgets.
Okay.
Is what we did, so yeah, as you can show these effects, through the latent cooling, and rain evaporation at the, near the surface is what's driving the cold pool, even though graupel sublimation is really important above. That's exactly what's driving it at the ground, but it's rain evaporation from melted graupel. It's not the warm rain falling.
Okay, that's really, so the cold pool is more intense or less so under enhanced CCN?
So they are less intense. I've actually got a cold pool strength here. For the well-behaved thunderstorm cases here in the model anyway, you can see as you increase the CCN, there's less cooling at the surface. Not as much response though for the supercell.
So awesome. Thanks, Sonia.
Oh, you bet.
Okay. We want to give people a few minutes for break before next session starts. So thank you for the presenters.
Juan, did you want to take a picture?
Yeah. Oh, yeah. Thank you for reminder. Yes, everybody turn on your camera and let's see how. Andre, you want to take it? I don't know how to get all the people. Maybe just display.
Please stop sharing. That will help.
Yeah.
I'm sorry. Can you? Oh, there it is. Okay, I was trying to find the button. It was on another screen. I'm sorry.
Okay, so now we have all the people. Now, let's see how to pay. Let me close. Okay. So we'll just take a screenshot. Andre, how did you do this? Is a better way. Andre, you're muted.
Sorry, almost done. One more.
Everybody smile.
Okay, we're good.
Okay, thank you so much. Yes, so let's take a 5 minutes break and come back on the over. Thank you. Mac and Dia.
Dia, are you there?
Yes.
Ah.
Yes, Mike, I'm here.
Okay.
You want me to introduce the speakers?
Yeah. Yes. If you can introduce the introduce yourself first, and then introduce the speakers. I'll for all our speakers, it looks like they're all here. I'll chime in at 9 minutes if just to give you a heads up that your time is running short.
Okay, sounds good. Hello, everyone. I'm Dia Wang from Brookhaven National Lab. And I'll be hosting the third session of the day, which is the Tracer Field Campaign. And we have 4 speakers for the session. They will be presenting some results using tracer using tracer data sets, and also some long-term statistics over the Houston region. So let's get started. Our first speaker is Christopher Toftedal. He's going to be talking about radar climatologies of tracked shallow and deep convective clouds over the Houston region. So Christopher, please take it away.
All right. Thank you. And you got my last name right, which is a fairly uncommon occurrence. So I appreciate that. So I'm Chris Toftedal, and as was mentioned, I'm going to be talking about some radar climatologies that I've been working on. So let's see. There we go. So as we all know, convective clouds have a large effect on your Earth's climate system. However, our understanding of what environmental factors control their initiation, lifetimes, and intensity is limited because of their rapid evolution. This rapid evolution makes observational data sets hard to obtain, and modeling these processes even more difficult. As we've seen today, the effects of aerosol particles on convection is still a subject of a recent study, and has been the subject of intense debate in the literature for at least the last 2 decades. So what we wanted to do is look at an area where there's pristine and polluted environments, which the coastal area for Houston, which is part of why Tracer and Escape are being performed in this region. We're using that location to use these climatologies in an attempt to address some of these outstanding questions, sort of in an indirect way. We're not looking at aerosol concentrations directly, but looking at to try to address some of these questions for a large number of convective cells. So how we did this is we analyzed KHGX, which is the Houston NexRad, as well as GOES 16 channel 13 brightness temperature for June, July, August, and September from 2018 to 2021, using a modified version of the MCIT tracking algorithm to track cells that initiated during local daytime. So the initiation had to be between 9 a.m. and 8 p.m. Central Daylight Time. Threshold variables were identified, and values for these thresholds were empirically derived from all tracked features in order to isolate shallow, modest deep, and vigorous deep convective cells from other tracked features such as large areas of stratiform precipitation, high clouds, and non-meteorological targets. So the threshold variables that we came to are the initial cluster fraction of the cell, or whether or not it's discrete at the time of initiation, the lifetime minimum GOES brightness temperature, the lifetime maximum vertically integrated liquid, the lifetime maximum radar-derived cloud top height. This next one is a little bit of a doozy, but I have a figure to illustrate it better, so bear with me. It's the lifetime maximum ratio of the radar-derived profile depth and cloud top height, or C ratio, the split or merge status of any given cell, and then lifetime maximum area for shallow convection only. So this figure here illustrates the C ratio. So in this example, we say, okay, we have a radar-derived cloud top height of 8 kilometers and a radar-derived profile depth of 6 kilometers, which would give us a C ratio of 0.75. This gives us a way to assess the vertical extent of these cells without having to specify a hard-coded value. And then we performed near-storm environment analyses using HER data. We used the hour preceding cell initiation at the location of cell initiation and obtained data from that for each cell that we analyze. This table shows the thresholds that we used. We wanted these cells to be discrete at initiation, We wanted shallow convection to have relatively warm brightness temperatures and deep convective cells to have relatively cold brightness temperatures at some point during their life. We wanted to make sure that there was some vertically integrated liquid, that the cloud top height for shallow convection was less than 8 kilometers, for modest deep convection was between 8 and 12 kilometers, and for vigorous deep convection was greater than or equal to 12 kilometers at some point during its life. The C ratio for shallow convection of greater than or equal to 0.6 and greater than or equal to 0.75 for deep convection. The lifetime maximum area for shallow convection could not exceed 30 square kilometers. This is to ensure that we're not looking at large areas of stratiform precip. We removed any splits or merges since these tend to complicate the processes involved with these cells. And that left us with over 38,000 shallow convective cells, 8,500 modest deep convective cells, and 5,200 vigorous deep convective cells, which allowed us over 100,000 volume scans for each case type. So in the next figures here, it'll be showing aggregates of the number of radar cells, radar volume scans, but when I show initiation locations, that'll be the number of cells to sort of orient you of what you're looking at. So to show you that we're looking at what we claim to be looking at, we have GOES brightness temperature here on the y-axis with colder temperatures to the top, and maximum vertically integrated liquid on the x-axis for shallow convection, modest deep, and vigorous deep convective cells. You can see our shallow convective cells remain in this warm topped Lowville region for the duration of their lifetime. And then modest and vigorous deep convective cells show this sort of backwards C shape. And I'm going to focus on the vigorous deep convective cells since it's the easiest to show this. But these cells form in this warm topped Lowville region. As they begin to grow, obtain higher and higher levels of Vil, get colder and colder tops, reach their peak strength at the mature phase here, where they're at their cold highest Vil values. And then as they begin to dissipate, move into this cold topped low Vil region, where we suspect we're seeing after convective core dissipation, we're seeing the leftover anvils. And then we can animate these looking at how these evolve over a given day. So we broke them into 3-hour chunks from 9 a.m. to noon, noon to 3, and 3 to 6, and 6 to 9 p.m. Central Daylight Time, which are shown in the animations here. And again, I'm going to focus on the vigorous deep convective cells since shallow isn't very interesting. It just sort of stays in this, again, warm top, low Vil region. And it's easiest to show this growth, mature, and decay phase in vigorous deep convective cells. So you can see here when the animation restarts, you start in this area of warm topped low Vil, grow upscale into the early afternoon into this high Vil cold top, and then moving into the afternoon and late afternoon and evening into this cold top low Vil region, which suggests that we're seeing growth from small cells to their most intense phase and then moving into dissipation. So where are these cells initiating? So these cells, as you can see, preferentially initiate along the shoreline for all 3 case types. One feature to note is that shallow convective cells show this preference to initiate to the southwest of the Houston metro, with potentially either enhancement to the southwest or suppression to the northeast of the Houston metro. That is not shown in your deep convective cases, neither modest or vigorous deep convection. So as with the plots that I just showed, we can animate these for the same 3-hour chunks. You'll see here in the morning hours, morning to noon, the initiation is confined very close to the shoreline and moves inland. Moving into the mid to late afternoon, initiation falls off considerably, and then we move into the evening hours where it's essentially very few cells are forming. This suggests that we're seeing sea breeze initiation with these cases. Another interesting feature of note here is in our vigorous deep convective cells, over the Houston metro in the late afternoon hours, we see a hot spot in initiation. We suspect that this is caused by urban heating, but haven't done analysis further to confirm these suspicions. What sort of environments are these cells forming in? So we have composite soundings here. The solid lines are your mean values. Your dot dashed are your plus or minus 1 standard deviation values. For profile path in black, temperature, environmental temperature in red, and dew point in green. Our wind barbs here in black are mean, red is plus 1 standard deviation, and blue is minus 1 standard deviation, and these values are in knots. So when we go from shallow convection to modest deep convection, we can see that the environment that the shallow convective cells form in is considerably drier in the mid to upper levels, but the low levels below 800 hectopascals are essentially the same in temperature, moisture, and wind profile. When we compare vigorous deep convective cells to modest deep convective cells, we see that the environments that they form in are essentially identical. So one more thing that I had mentioned is this bias in initiation to the southwest of Houston. So to analyze this, as you can see by this map here, we isolated this region near the coastline and used days where the shallow convective initiation count surpassed the 95th percentile for all shallow cases. This allowed us just shy of 3,600 cell initiations to the southwest and just over 3,000 to the northeast. And then we performed the same near storm environment here analysis here at the time of initiation. So this first SKU-T diagram shows that full strip, that's full subdomain. And then we normalize the cell initiation count by the area of the domain. So you can see that value up here at the top. When we go to and look to the southwest of Houston, you can see that there's a hint that the mid to upper levels are slightly drier. That cell initiation normalized by area is slightly higher. And then when we look to the northeast of Houston, we see that there is slightly more moist mid to upper levels, but definitely a decrease in cell initiation normalized by the area. Going through these three again, you can see though, the environment that these cells form in is nearly identical. So to summarize, to summarize, the observed cells exhibit initiation that is primarily driven by the inland propagation of the sea breeze. Shallow convective cells form in environments with drier mid to upper level moisture when compared to deep convection, whereas the two deep convective types form in environments that are nearly identical. The cell types form in environments with nearly similar near surface and surface temperature dew point and wind profiles. Shallow convective cells preferentially initiate to the southwest of the Houston metro, which is a relatively pristine environment. You're seeing mostly the most aerosols that would be there would be salt from the propagating sea breeze, where to the northeast, upwind of Houston, you would see more anthropogenic aerosols. Is this what is affecting or suppressing shallow convection? We're not sure. The environments to the southwest and northeast are quite similar, but the southwest does appear to have slightly drier mid to upper levels than the northeast. So with that, I will take questions.
I would like to see actually the same analysis for the adjacent sea area and to see the effect of the land breeze overnight and difference, systematic difference in the cell properties over land and ocean under same thermodynamic conditions.
So we haven't looked overnight. Yeah, we haven't looked overnight. We have done daytime differences in land versus ocean. Over water, the near storm environment tends to have higher values of CAPE by almost 1,000 joules per kilogram.
Christopher, I have a quick question. So, yeah, very nice analysis. And we are actually also very interested in the precipitation heterogeneity among different parts of Houston, and trying to explain why we have this heterogeneity. So from your analysis, it's showing that in the west and the northeast there's it would be interesting with model simulations. We're trying to dig out the reasons. But one of the comments is that I think from the same dynamic, meteorological environment, it suggested that other physical factors could play a very important role.
Exactly, yeah. And it seems to be some of the analysis that we've done just numerically seems to there is sort of a difference in initiation where to the southwest of Houston, deep convective cells more preferentially initiate, but it's not as strong of a signal. And you can see that by the initiation map as the shallow convective cells.
Yeah, well, yeah, have to talk about more on that. For Jason, we'll work on the model simulations on that. Thank you.
Thanks a lot, Christopher. I think we need to move on to the next talk. So our next speaker is Sean Freeman. He will also talk about some tracking results, but using both model and observational data sets. So Sean, the floor is yours.
Thank you so much for the introduction. Before I begin talking about this tracking library that we have built called back, I want to acknowledge the contributions from the many, many collaborators in all of this. This is an effort that originally came out of the ACPC group and has now grown to include collaborators from Oxford, Tropos, even Gothenburg in Sweden, Texas Tech. It's been a really fantastic collaborative project, and the DOE at Argonne. So TOBAC, for those of you unfamiliar, is a Python package that's primarily designed to objectively identify, track, and analyze clouds. And this originally came out of Oxford and CSU, and it was released originally in 2019. And I'm going to talk a little bit about TOBAC in general, but also some of the results and some of the developments that we've made since then, getting towards version 1.5. So this is an example over here to the right, just an animation showing some of the power of TOBAC. On the background is a very large domain, high resolution simulation from a numerical model, here in this case, the RAMS model. In the background is integrated total condensate, and on each of these individual dots is a place where TOBAC has identified and is currently tracking an updraft from the model, and it's colored by the updraft strength. And so I'm showing a model here, but one of the biggest advantages of TOBAC is that it can work on any gridded data set. It doesn't care what your grid is, doesn't care what your variable is. It will work on any gridded data set that you give it. And it can identify and track features in 2D, and now starting in version 1.5, it can track in 3D, meaning X, Y, and Z, and time, of course. Which means that it can be used for all different kinds of data sets on all different kinds of scientific problems. And then using those tracked features that can then identify 2D areas, regions, or 3D volumes of other variables, whether that's the variable you're tracking on or whether it's the variable that you're not tracking on. It can even do this across different grids, which I'll show for an example later. So why TOBAC? I kind of got at this a little bit before, but TOBAC is what we call input variable agnostic. And in fact, it's not just for clouds. It really doesn't care what your input variable is to be able to track it. It doesn't rely on anything specific. For example, there's been various things in literature or things that we've done showing tracking on clouds and updrafts in model data. It can track on storms using radar reflectivity, clouds on infrared brightness temperature, clouds on lightning in satellite data, and even haboobs on dust concentration. We've seen many other examples of this outside of kind of the cloud area, as people are using this to track trace gas data in large simulations. And so the fact that TOBAC will allow you to use the same package to track many different things on many different grids is really what gives it its strength. So I want to talk about each of the individual little features of TOBAC as we get into it. So first off is this, what's called feature detection. This is the first step that TOBAC takes to be able to identify individual clouds or individual features of interest. So feature detection gets a single point in 2D or in 3D from an input gridded field of any variable. So this is an example here of radar reflectivity this is at 2 kilometers above ground level. This is just showing it, in 2D mode. And it's identifying each of these individual little convective features from just using reflectivity. It can derive this single point that it identifies by thresholding on either the maxima or the minima, and then it uses a weighted average or many other different methods to find a single point from the mask. And in the end, you end up with this tabular format data called pandas. This is a Python package that has just saves tabular data. It can even output as an Excel if it wants to. It's very similar to Excel. It can be exported to CSV as well, or HDF5. And this is going to give you the locations of each of the individually detected features from TOBAC, and a little bit of statistics about each of the individual detected features from TOBAC. And additionally, this is originally only in 2D, but now works in 3D as well. Version 1.5, which is going to be coming out this summer, has a support for 3D and periodic boundary detection, periodic boundary feature detection and tracking. And what we mean by periodic boundaries here, if you have an idealized simulation with cyclic boundaries, that's going to be supported. Or if you have a global simulation, it won't quite work over the poles yet, but it can certainly work in a band around the, around a certain region. If, for example, you're interested in tracking along the tropics, you could track along the tropics using this new periodic boundary detection support that's coming in version 1.5. So for an example of the power here of being able to track and feature detect in 2D and 3D, this is what it looks like. This is a XY cross section of a from LES simulation showing various updraft velocities colored by the updraft velocity shown here. This is the entire column that's collapsed down into a single 2D using the maximum values. And so you can see you end up with some features that kind of get squished together. And when you start to look at this kind of same area in the XY cross-section at a single level, in the XZ cross-section and the YZ cross-section, you start to see that we are able to capture more structure by knowing that Z information in TOBAC and being able to support, being able to track these features in 3D. So using those 3D or 2D to track features, you can then segment out on the data, which basically means that you can identify whole regions or volumes of data from those initial features and are associated with those initial features. So this is an example using the same data set here. This is the same data set I showed before, radar reflectivity that's gridded with each individual feature identified. And on the right-hand side, you can see these outlines here are showing the 2D surface areas that are associated with each of the individual features. Which is a really powerful tool, especially if you're interested in how the entire volume or the condensate load or things like that change over time. So coming in 1.5 to segmentation is the ability to combine data sets. This is a different example. Again, this is a gridded radar reflectivity at a single level, and each of these little gray dots here are the locations of the identified features. But that doesn't give us anvil size. And so one of the features that's coming in 1.5 that we're really excited about is the ability to associate each one of these individual features with data on a different grid entirely, using any gridded data sets for segmentation. So this example here just shows the same area, the same region, and each of these dots is in the same location because the dots on the right-hand side, which is from GOES 16 infrared imagery, these feature locations were identified by the radar data, and then yet we were able to segment out each of these individual little anvils from these convective cores and associate the anvil region with the convective cores detected by radar, where the anvil is detected by infrared data. And TOBAC will now do all of the regridding for you that's coming in 1.5. So, and I talked a little bit about tracking earlier. This is what ties our predicted features together with time. And I mentioned that this has support for periodic boundaries, but just to demonstrate what we mean by this, this is basically a simple example here showing a artificial model boundary. This is a cyclic model, meaning that if you cross this boundary, it should be able to continue to track along the boundary, whereas the original TOBAC didn't do this, and now starting in version 1.5, we will have the ability to track across boundaries, and certainly global tracking, including over the poles, is something that we're targeting in the future. Tracking outputs a pandas data frame again. This is the tabular data format that has information about every feature that is detected and tracked by TOBAC and its linked features. And then you can bring this information with segmentation to produce full volume or region statistics over time with the entirety of the cloud. I think one of the most common questions we get is, what is the time difference that we have to have for the data to be able to track effectively? Depends on the data, and it primarily depends on the feature spacing and the movement speed. If your features don't move much or they're pretty far apart, you can have a longer delta T in your data than you can in other cases. So looking at the performance, and this is another thing that we really focused on with TOBAC version 1.5, and this is already actually in, these improvements are actually in 1.3 now. So on both of these cases, on the x-axis is number of features, which is approximately equal to the number of times that are run in terms of time steps that are run from the input data. This is from a GOES 16 case. And on the y-axis is the total time taken in seconds. The blue line is TOBAC version 1.2. The green line is TOBAC version 1.3.0. And you can see that in feature detection, we have increased our speed dramatically by up to 100 times over TOBAC version 1.2 in the newer versions. We can feature detect on a full day of GOES 16 data in just a couple of minutes now instead of an hour or longer. And tracking is also improved really dramatically, and this doesn't even show the full extent of it. Tracking grows in 1.2 of TOBAC grows exponentially in terms of the time taken, whereas the newer version does not grow exponentially. So in the GOES 16 example here, it decreases our total tracking speed from several minutes to a few seconds. But in the very large RAM simulation that I showed before, it decreased total tracking time spent from months to just a few minutes. And so tracking and feature detection now scale really well and perform really well, even on really large data sets. So overall, TOBAC allows us to look at individual atmospheric objects and track their entire life cycles, whether that be a cloud, a haboob, a trace gas plume. It really doesn't care what your data is, and it doesn't care what object you're trying to track. It can allow us to be able to identify that object, whether it be clouds or something else, get the volume or the region of the cloud, and track them throughout time. And it can now, with the addition of some of the new features in version 1.5, can bring disparate data sets together to be able to understand clouds top to bottom. And so, as I mentioned, TOBAC version 1.3 is now available online. It came out a few weeks ago. We also have a new URL that is github.com/tobac-project/tobac. If you have the old URL, it will redirect automatically, but we've now consolidated our TOBAC efforts under one project. TOBAC 1.5 is in progress. The 3D and periodic boundary changes now are available as a pull request if you're interested in trying them out earlier. I mentioned the collaborations with Texas Tech. They're planning on adding merger and split support to version 1.5. We also have some contributions from Gothenburg in Sweden to add smoothing of the data and spectral analysis of the data before it goes into feature detection. And we encourage all of you that are interested to join our development efforts. We have a fairly active GitHub in terms of issues and pull requests. And if you're interested, either contact us on GitHub or email me, and we'd be happy to set you up and get you started. So thank you.
Thanks a lot, Sean. This is a very exciting upgrade of TOBAC. So does anyone have questions for Sean? I see a question from Ed. Do you want to unmute yourself and ask the question? Okay, I will just read the question. So what was the update you made to improve the tracking times? A better search through your features or something fancier?
Yeah, so actually the updates to improve the tracking times were mostly accounting related. We had some issues in the original version of TOBAC where just the accounting of each individual feature and doing the actual data formatting and doing the data connections was a lot slower in TOBAC 1.2, and we fixed a lot of those issues in TOBAC 1.3. We actually made it so that the results are identical between 1.2 and 1.3 in terms of feature detection and in terms of tracking, which means that using TOBAC now, I highly encourage you to upgrade to TOBAC version 1.3, and you shouldn't notice any difference in terms of what your data output looks like, which is really exciting.
Yeah, sounds great. So, further questions for Sean?
I think we should probably move on.
Okay, let's move on to the next speaker. So our next speaker is Maria Zvadovic. She's going to talk about some very first results using tracer observations about aerosol particles. So Maria, please. So we see two screens here. Yeah, I think we're good now. Yep.
Yes, thanks, Dia. Hello, everyone. I'm Maria Zawalovic. I'm from Brookhaven National Lab, and I'm going to switch gears a little bit and talk to you about aerosols. So the tracer campaign has been ongoing in the Houston area for about 6 months now, and I've been looking at the aerosol chemistry data primarily just to develop a bit of a picture of what the conditions are like as we head into the IOP, so that we know what to expect. So the collection of instruments that I work with is currently deployed at the AMF1 site in La Porte, Houston. And let's quickly the laser pointer right here. We sample from the C-tainer called an AOS, or an aerosol observing system. We sample the aerosols from a 10-meter stack it travels into the container where we have instrumentation racks filled with various kinds of aerosol instrumentation. And for me, my primary focus is the instrument that you don't actually see in this photo, but it would be below the CCNC right here, called an aerosol chemical speciation monitor. This is an aerosol particle mass spectrometer, which quantifies something that we call non-refractory aerosol composition. A key step in ACSM's sort of measurement flowchart is that it samples aerosol, introduces them into a high vacuum region, and then it impacts them on a very hot 600 degrees C surface. So any aerosol constituent that vaporizes at this temperature, we can observe. But things that don't vaporize at this temperature, such as dust or black carbon or sea salt, we do not observe. So that's what we mean by non-refractory. The particles that we see best are from 100 to 500 nanometers, though we see particles with a bit of reduced efficiency all the way up to 1 micron. So we consider this as sort of a PM1 instrument. Something that's a limitation of this instrument is that the ionization of aerosol particles happens with this electron impact scheme. We shoot electrons at the aerosol vapors. And what this does, it fragments the constituents of the aerosol into very small fragments. So there is a bit of a non-specificity inherent in it. For example, we can't tell what's exactly in the aerosol, but we can guess by using very statistical analysis that I will show. We can guess at the source, but it is not a perfect science. So we quantify, so an ACSM quantifies aerosol mass, non-refractory aerosol mass, and it is speciated into generally these four categories, plus chloride, so 5 categories. And we use a combination of calibrated, we use a combination of this mass spectrum as well as some calibrated quantities to convert the spectrum to a mass concentration. And so finally, here is some initial results from the tracer ACSM. And we have put it online and just at the end of September for the beginning of the tracer campaign. And I've analyzed data all through the beginning of April. So far, we had no major interruption in the data flow. So the ACSM data, as you see here, is has been also processed by the ARM ADC and is available. I'll show a link later. Something that we, some data quality parameters we look at are, for example, this ammonium balance. So we see now that the aerosol here is neutralized, which is a feature of polluted boundary layer. We observe a high peak in the winter in nitrate, which is consistent with deposition of gas-phase ammonia and nitric acid onto the particles. And we also see that the ACSM volume, aerosol volume concentrations close well, track well with the SMPS. So here are some plots of diurnal cycles. We average all the observations and plot them as time of day. This is organic, this is sulfate, nitrate, and ammonium. And we see distinct patterns in organic and nitrate, which suggest sort of a very local pollution, and it tracks well with the boundary layer height. Something that I like to do when analyzing this type of data is to look at non-parametric wind regression plots. So we correlate these chemical constituents in the aerosols with the wind direction and speed, and we see something that the diurnal plots also show is that this organic and nitrate constituents are very local pollution related, and they mostly high concentrations happen when the local air is stagnated. Now sulfate is slightly different, and we consider, in this specific case, we consider the sulfate as sort of a long-range transport tracker of air that comes from slightly further away. And when we actually look at the trajectory analysis, this is from HighSplit, we see also organic and nitrate being somewhat local. But now sulfate, we see a lot of influence from the coastal regions, from the Gulf, as far as Mexico. And I've talked about this a little bit in one of the recent tracer calls, and we actually brought up that this could be long-range transported biomass burning aerosol because there were a lot of fires in this Yucatan region here. Some further analysis that we do of the individual ACSM mass spectra is to use positive matrix factorization, which is a statistical technique that pulls out spectral fingerprints or source profiles and is able to track the aerosols down to the source. But we do need to be careful because aerosol mass spectra and chemical compositions change with the residence in the atmosphere. After the aerosols have considerably aged, we can no longer tell the difference between the sources. So we've applied positive matrix factorization to tracer data, and I'm happy to speak about how we did this exactly. And we pulled out 3 different factors: biomass burning factor, a hydrocarbon-like factor that we consider traffic-like, and something called low volatility or oxidized organic aerosol, which is this very oxidized spectrum that all aerosols manifest after they've been in the atmosphere for sufficiently long. So basically aged aerosol. Now, if we look at some diurnal cycle, the biomass burning factor shows this very local influence that tracks opposite with the planetary boundary layer height. The hydrocarbon-like, the traffic fuel combustion type factor shows some increases where we expect traffic, which is generally what we expect. So at the beginning of the day and as well at the end of the day as well. And the aged aerosol from any source doesn't really show a pattern as it could have come from a combination of these local sources as well as the long-range transported ones. We can correlate these factors to other observations that we take in the AOS, such as the ethylometer or the CO2 or carbon monoxide, to sort of and the correlation between the local pollution factors and black carbon and carbon monoxide strengthens is additional evidence for what these factors are. I've done a non-parametric wind regression on these factors, and they also show a very local influence with the LVOA possibly also coming from further away. And I'd like to mention that the 2 observations that I've taken into account here that don't correlate well with the pollution factors BBO and HOA are sulfate and ozone, which, because sulfate is in this case a long-range transport tracer, and ozone is in this case very interesting. We think that ozone in the winter is not necessarily produced photochemically, but rather comes perhaps from something like a dry intrusion, which would be interesting. And we actually expect to see more photochemically produced ozone as we go into the summer tracer.
1 minute, Maria.
Yep, so I am already done. So thank you for listening. And here, all the ACSM data that I've shown, apart from the PMF analysis, there's some data discovery now. I'll take questions.
Thanks a lot, Maria. I think we have time to take one quick question.
Andre, just a quick comment. I don't think it's very plausible that your sulfate comes from biomass burning because, for one, typically biomass burning doesn't release a lot of sulfur. And the second, you also have basically no correlation at all between the biomass burning OA and the sulfate. So it must have a different source. And you might just want to look into global databases on SO2 emission and look for some sources there. It might be oil processing, fossil fuel processing, that sort of thing, or I don't know, maybe even a volcano down there.
Yeah, could be. We should investigate that one more, a bit more. Also, possibly coastal marine.
Yeah, that's of course possible as well.
Thanks again, Maria.
Yep.
And let's move on to the next talk. So our next speaker is Ruslan Optum. He's also going to show us some observations during tracer field campaign using stereo camera. So please take it away.
Thank you. Hello, everyone. Today I will talk about our data product on clouds during the tracer campaign. Okay, I just started the slideshow. So on this data product, I'm working with David from Berkeley and Scott from BNL. Let me start by talking about the setup. So this is the aerial map of the aerial map of the region. Here is the AMF site, and this is the main site where the tracer, many of the instruments of the tracer campaign are located, and our cameras are located, across the AMF site, about 12 kilometers from the AMF. And we have those two cameras. They are facing west, and they have, they are facing west, and they have a common field of view of about 60 to 70 degrees horizontal field of view. So this extends from around the AMF side about 8 kilometers in the south-north direction. So by using those cameras, we are collecting synchronized pictures at 20-second intervals during the daytime. And we are using machine vision algorithms to generate what we call point cloud of cloud points, PCCP in short, from cloud features. Because we are relying on cameras which run in the visible band, and we are relying on machine vision algorithms, in order for us to collect the data, the cloud features must be seen by both cameras. And by feature here, we mean that we are referring to pixels which are distinct from their surroundings. So, for example, in this picture, the regions encircled with those blue lines are ideal for our algorithms because they are crisp, they are not blocked, and they are very distinct from their surroundings. But on the other hand, the regions that are encircled in red, they are the points, the pixels inside are not distinct from their surroundings. As a result, they are not ideal for our algorithm. They cannot be either retrieved well, or they cannot be retrieved at all. So by using this algorithm, what we get is, as I said, PCCP. PCCP is basically the coordinates, 3D coordinates of the features that we could capture. And here is how it looks for one certain moment of time for this image. This is quite an ideal image. We have two isolated deep convections, or medium to deep convections. And with respect to the camera field of view, that's how it looks on a 3D map. those are the coordinates, and the AMF location is marked here. So when the conditions are ideal like this, we get like tens of thousands of points at a time. And so we can actually observe the evolution of a convection if they are in the field of view of the cameras. This is something, this is how PCCB looks for shallow clouds. We get, this is also again, sort of ideal conditions, although we have some of the clouds are blocked, but still we can see the ones that are in the field of view of the cameras, and we get thousands of points at a time from this instant. When the conditions are good for the visibility is good for the cameras, for shallow cumulus, we can generally get a field of depth about 10 to 15 kilometers from the cameras. And for deep convections, we can get like a bit deeper, like 20 or even 30 kilometers field of depth. But of course, if there are low clouds, they may be blocking the ones that are in the back. Now I will show you some plots which summarizes the content of the PCCB product for a day. We made this product so that it will summarize the day in 3 time intervals, from morning, early afternoon, and late afternoon. So in the leftmost plot, we see a picture which is right at the center of this interval, this time interval. And when we project all the cloud points onto the height axis, we get the distribution of cloud points in the rightmost axis, and which gives an idea about the cloud situation in during that time. For example, from here we can see we have some clouds forming. The cloud bases are forming at around below 1,000 kilometers, and we see that there is some convection forming because of this distribution, and the animals are forming at around 5 kilometers. And in this middle panel, this is the distribution of clouds on the horizontal distribution of the clouds with respect to the AMF location. This is from the field of view of the cameras. That's why this is towards north and towards west, so that it is compatible with this picture. We can see that there is some convection happening, but it's not like not right at the AMF side, but it is kind of passing around the AMF site. And of course, the color bar here also indicates the height levels of those clouds. And of course, those are the ones that are captured by the camera. I should point this out. And for this day, for this particular day, we can see that in the early afternoon, the clouds the shallow clouds start to diminish. And we are seeing those high clouds, and later in the day, we are just seeing the animals that are forming at around 5 kilometers, and there are also higher clouds in the 8 to 10 kilometer area. This is just another picture for another day where we see again the shallow clouds, which are getting as deep as 4 kilometer heights, and early afternoon we see the convection forming, deeper convection forming around the AMF site for that day. Although this is not related to clouds, this is something else I want to show that that's within the capability of the stereo cameras. This is a sample where we have industrial plume forming at this site. It is about 4 kilometers to the south, and I think about 1 kilometer to 2 kilometers to the west of the east of the AMF site. And we are able to, although this is not fully automatic as the cloud detection, we are able to detect the plume, and we are able to see how this plume is evolving and whether it is passing over the AMF site and so this shows the height it is, and its location and height with respect to the AMS side, and this is again the horizontal view. So the movies of those from those cameras can be accessed either through the tracer dashboard or the ARM data archive from this address by just typing StereoCam. And if you have any questions after this talk, or you need to ask more, you can reach me at this email address. Thank you.
Thanks a lot. Thanks a lot for the great talk. Any questions for Ruslan? Mike?
Yeah, Ruslan, thank you for the talk. I think these are a great complementary measurement to some of the other things we're collecting during Tracer. I know that you and David have done some work retrieving vertical velocity or cloud growth factor from these measurements. Are you expecting to do that for the Tracer campaign also, at least for isolated convection maybe?
Yes, exactly. For isolated convections, we could capture very, very few of them for the past, because the cameras were deployed at the end of August, and starting from September and up to this time, we didn't have really very nice cases from that point of view, but we are getting ready for the season, actually. Excited to have good cases that we can work on.
Yeah, great. I see this very complementary to some of the tracking stuff that we've seen already, and the vertically pointing measurements at the ARM site. It kind of helps connect some of those dots a little bit. So hopefully we could pull all that together.
Yeah, if we can find something like that, the one you can see in the if we can get more of those cases, it will be great. Yeah.
So I see a question from Ed again. What's the accuracy at 30 kilometers for the deep convection?
So it's around 50 meters. I think they are talking about the questions about the resolution of the PCCV product. It is around 50 meters. Well, at 30 kilometers, it must be, 50 kilometers is around, 50 meters is around 10 to 15 kilometers. So at 30 kilometers, it will be a little bit less, but let's say 50 to 100 meters.
Yep. I think we need to wrap up here. Mike and Jeevan, you have any notes to the audience?
Yeah, thank you, Dia. I'll say something first and then let Jiwen add. But I want to thank all the speakers for a great set of talks and for keeping on time very well today. I think this is very interesting. I know today we were very heavy on talks. Tomorrow we'll have a lot more discussion. So we'll have some flash talks with kind of poster sessions, which we've dedicated an hour of time to. And then we have another hour of discussion where we'll talk about some of the next steps for our ACPC analysis, tracer analysis, and where we go from here. Jiwen, I don't know if you have anything you'd like to add.
Nothing particular. I just want to mention for post presenters, please remember to set in your one slide summary for tomorrow morning. Yeah, it's morning to me, very early morning for others, different time. Yeah, also I would like to echo what Mark said. Thank you, everyone. And also thank you, Andre, for helping us on this. See you tomorrow.
Yes, thank you. Danny or Mingwei have anything?
Yeah. Okay. So, but tomorrow we'll have actually 3 minutes per talk, so it can be more than one slide. but not much more than that. Well, and just second, Mike, about the quality and the relevance of the talks to ACPC, and look forward to the continuation tomorrow. So thank you.